All right, I'd like to introduce our next speaker, Kate Sturge from University of Maryland College Park in the field of materials physics. Kate is an LRGF fellow, and she has done a residency at Los Alamos National Laboratory. So thank you, Kate.
Thank you. All right, good morning. Hi, I'm excited that I get to talk a bit about some of the highlights of my PhD research, which pertains to the dynamics of fast electrical breakdown inside of electron-charged solids. So electrical breakdown or dielectric breakdown occurs when a typically insulating medium becomes spontaneously conductive due to extreme electrical stress. And usually the way that people study this in the lab is by applying a high voltage across their medium with some sort of external electrode setup. But we do things a little bit differently in my lab, where we actually impose a very high internal electric field by charging up the material with electrons. And so what that looks like is we put a about 1-inch thick piece of polymethyl methacrylate, or PMMA, or acrylic in front of a 5 MeV electron beam. And at this energy for that thickness of material, the beam implants itself roughly midway through the sample. And so you end up with a very high internal negative space charge density inside of your acrylic. But since we're doing this in atmospheric conditions, positive ions that are produced by the electron beam cling to the surface of the material. So you end up with a very high internal electric field, even though the object is net neutral. There's no external electric field, but there is a very high internal electric field. So while the space charge density generates a very high electrostatic field inside of the material, it's not on its own necessarily enough to cause breakdown to occur, which is good for us because that means we can control when breakdown actually happens and study its effects. And so the way that we initiate breakdown is just by applying a local field amplification to one surface of the material. And that can look as simple as just hitting it with a sharp stick or something of that nature, where you are pushing the electric field in the vicinity of the point driven into the surface to above the breakdown threshold of the material so that an avalanche breakdown can occur. And in a sample that you can hold in the palm of your hand, the whole process takes roughly 100 nanoseconds and leaves behind a beautiful damage pattern inside of the material known as a Lichtenberg figure or electrical tree. And so those figures are really pretty. They make nice desk ornaments, but there are practical reasons to study them. The main reason we study deep dielectric charging, or the process of charging your insulating volume with electrons, is spacecraft charging. So this is something that happens on satellites and spacecraft in the high charged particle radiation environment, where charged particles become embedded inside of your spacecraft dielectric. And if that electric field increases to above the breakdown threshold naturally, due to continued charge accumulation, a rapid electrostatic discharge or breakdown event will occur. And that damages your dielectric, but it can also catastrophically or temporarily damage surrounding electronic components. So that's why we study this. And so one of the ways that we study this incredibly fast phenomenon, so like I said, in a small sample, it occurs in about 100 nanoseconds, is by high-speed imaging at Los Alamos National Laboratory. So LANL has a very unique camera that is capable of taking images at a frame rate of 1 billion frames per second. And so that means that we can image the actual breakdown evolution inside of our samples with a nanosecond temporal resolution. So that's exactly what we did. We charged up about 4-inch by 12-inch by 1-inch acrylic slabs with our 5 MeV electron accelerator, and then transported the charged slabs to LANL, where we were able to complete our experiment. And so there's a few things that I want to point out. For the purposes of this talk, we got a lot of data through this experiment, but there's only a few things that I have time to go over. The first is that the breakdown inside of the material progresses as a circular front. So it initiates over towards the left side of that video frame, and it expands circularly outward into the charged material, with all of the breakdown activity occurring in a very narrow band around the propagation front edge. The other thing that is important to note is that the interframe time here in this about 5 centimeter segment is 3 nanoseconds. So our speed of propagation starts at over 1 million meters per second inside of the material. So that's over 1,000 times faster than the speed of sound in the material, which is extremely fast. However, while it starts really fast, it doesn't maintain that speed the entire way, which is a conflict with previous models. The velocity actually decreases in time, and with the direct high-speed imaging measurements we made at LANL, we were able to track that propagation over time, where the front growth is in black and the measured velocity from that growth is in red, where it decreases to around 0.5 millimeters per second over the course of those 12 inches. And then finally, the last thing that I want to point out that's important for the rest of this talk is that the discharge current that you measure during the breakdown can be reconstructed using only the geometry of the breakdown progression and the measured dynamics information. So you end up with like a kind of complicated equation up at the top that's simply the geometric representation of the front propagating into this rectangular material, using the measured front radius and the front velocity over time. And we're able to match that very well to the average discharge current that we measured for all of these shots. And that's what the black line is. That's our actual measurement. The red dots are the fitted equation from up top to that curve using only a single fit parameter, which is the charge density at the front. And that's important because if you can measure, or if you can reconstruct the front dynamics using, or if you can reconstruct the discharge current, using only the front dynamics, then the reverse should be true. And so instead of doing this very costly and time-consuming experiment at LANL, where we directly measure the breakdown propagation, we can get similar information using only the measured discharge currents. And so that's what we did here. So one of the issues, the qualms that I had with the high-speed imaging experiment is that we were using rectangular samples for something that is circularly propagating, and that's just annoying and messy. And so I wanted to look at disks because, physicists, we like circular symmetry, and so that's what we wanted to do. And so we took these large acrylic disks, all 1 inch in thickness, ranging in radii of 10 to 40 centimeters, so almost a meter in diameter, these like large disks. And charge them up with 3 different incident charge densities so that you have various internal electric fields inside of the material. And then we initiated the breakdown from the center of the disk and measured the discharge current. So I have a video of that experiment. This is one of the mid-sized disks. It has already been charged. The accelerator is behind that wall here, so it's just coming out, and we are going to measure the discharge current. So it's resting atop an aluminum plate. And then Bram and Ethan, who are other people in my group, are lowering a top aluminum plate onto the disk. The little cage at the center, right here, houses 2 current probes with complementary frequency bandwidths to measure the discharge current. I whack that button, it releases the pneumatic tube that strikes the sample in the center, which discharges it, and we can measure the current. And so you end up with your electrical tree left behind in the material. All right, so once again, too much data, too little time, so just flying through some highlights. First is that in the low charge regime in the largest disks, the electrical tree does not extend entirely to the edge. They all stop at roughly the same distance, the same diameter inside of the sample. And that is reflected in the discharge current waveforms, which for the red, green, and blue are roughly on top of each other. The slight discrepancy of the red curve does correspond to a slightly smaller electrical tree, which is good. Second thing is that in both of these low charge and mid charge regimes, we see an approximately linear rise, and then the current transitions to this sort of level top behavior. And that's not something we had seen before, simply because we hadn't looked at samples this big before. It's only something you get at very long times. However, in the high charge regime, we don't see that. We just see a continuous increase until it reaches the edge of the sample, at which point the current decays. And so going back to that idea of backing out the front dynamics based on the discharge current, now our equation is a lot simpler because we have nice symmetry, and we get this complicated plot, which don't worry too much about it. But the point is that you have a velocity that starts once again at around 1 millimeters per second and slows gradually as a power law with time. However, in the 2 lowest charge regimes, you see a little bit of a transition here, where something is happening to the plasma behind the front that is causing the electric field at the front to decay even more rapidly until it eventually stops. And we can compare this to the high-speed imaging measurements, and we see really good agreement when we map the rectangular geometry to a circular geometry, which is promising. All right, so I want to emphasize, this is weird. This is strange electrical train behavior. So like I said, usually people study these in labs by applying a high voltage across their medium. And what you end up with when you are growing your electrical trees in this behavior is a growth that is on the order of like microns a minute instead of like millions of meters per second. So that is a huge discrepancy in terms of just the velocity of the breakdown. And it turns out that's because the high voltages you can achieve in the lab are just not nearly as much as you can achieve inside of your sample. And so the way that breakdown usually occurs is by this cumulative degradation, where you have a high energy electron breaking your polymer and creating this sort of network of gas-filled bubbles that form to become the network of electrical tree channels. And so with our very high electric fields inside of our material, it indicates that there's an entirely different mechanism happening. And so what I think is going on is actually impact ionization. And the reason I think that is because the reduced electric field, so the electric field inside of our material divided by the density of the material, is the same as what you get for an electrical breakdown in air. And I like to show this picture because that's me in the cage. Yeah, but anyway, so the gigavolt per meter electric field inside of our sample at the field amplification point divided by 1,000 times the density of air, which is the density of our material, is the same as the breakdown threshold in air. And so that leads us to believe that the similar mechanism can be occurring. However, there is some debate over whether or not impact ionization, which governs the breakdown in air, can actually occur inside of a solid material because the electron mean free path is much smaller. And I would argue that yes, that it actually can happen. The main reason is because during electron irradiation, the polymer is broken into pieces. So you sever that main polymer chain, and you also break off the side chains. And then you get very large radicals produced that then further decompose to other gases such as carbon monoxide, carbon dioxide, methane, and more. And so you have this slightly more porous material with trapped gases inside of your material, which increases the electron mean free path. So in summary, electron irradiation is important for allowing this process to occur because, like I said, you get increased porosity and gas-filled voids. You also have a very high density of shallowly trapped electrons inside of your material, which are needed to facilitate an electron avalanche in the first place. And then finally, you have a very high internal electric field, which is further amplified by applying that mechanical insult, that mechanical tip to the surface, which brings it to roughly a gigavolt per meter. And so, like I said, the internal electric field in our sample divided by the density, the reduced electric field, in other words, is the same as the electric field breakdown threshold of air. So it makes sense that our velocity is comparable to that of electrical breakdown in air, and that it makes sense that the breakdown mechanism would be similar. So just sort of in conclusion, the dark patches are the things I've been able to talk about. Other stuff we've observed that I don't have time for. But kind of the main gist is that this provides a new way of looking at electrical treeing in electron-charged materials that hasn't really been considered before because we were too busy thinking about how this is typically done inside of like an external electrode configuration. And it's just a totally different regime. So we have to shift how we're looking at it. All right, so in conclusion, thank you for listening. I really appreciate all of the help that my colleagues at Los Alamos have given me, as well as my wonderful group at the University of Maryland, and then obviously the Krell Institute and everything you guys do to support this work. So thank you, and I'll leave it here.